last class. This is a sine PW. Remember what I proved here. For example, the V11 is for the half bridge is the MA times VDC over 2, and for the full bridge is the MA times VDC. And I went through that, similar triangles and those kind of things. How did I prove it? And I assumed the V control is constant. If you remember, if you go look at what I did, I assumed the V control is constant. But basically, what it comes to your mind is that V control is not constant. This is sinusoidal, right? So how did he consider it constant? I'm saying, look at here. This is a VTRI and VCon on top of each other. Do the same graph. Just zoom in wherever you want. For example, I can zoom in here, here. I like here better. But for example, we can zoom in here. For example, even this is not a very high frequency. This is 6 kilohertz. 100 times of the control. Let's zoom in here. This is one of the worst places here. You got here? This is the worst place here. This is a V control, right? And this one is not broken triangle. This is because of the sampling time I have in my simulation. It should be perfectly a triangle, So my point is, look at here. Yeah, if you look at here, this one is not exactly matching down that end, but this is again like a 3 cycles, right? We can consider this one almost constant. We call it V control, and we use the equation and we prove that. Now the next thing I want to go over it. Let me go open the other one here. I'm going to put them online. I talked to Professor Mohan. This is from his book, and we are good to go with it. I'm going to put all these slides on. This is for chapter 8 from his book. It's a very good book. What we went over. We should have a. Presentation mode. So forget here. Oh, this is the half bridge we talked. Remember, this is the half bridge. This is the VD1 and this is the source here. This is the leg A switch anti-parallel with the diode. He derived this because later on he's going to use it for a full wave, full bridge, and 3-phase. They are going to be all similar. He's drawing it this way. And this is what we had for the harmonic system. Remember? We have a V control, we have a VTRI, and this is the VAO, the output voltage bipolar. Positive, negative, positive, negative. And this is a harmonic spectrum. If you look at the table I gave it to you guys, a copy, and it's going to copy. Is in one of the slides of this one. Does everybody have this table from the last class? This is everybody has. Nobody will have it. Here, this is a bipolar switching. Look at it very carefully. This is a harmonic number 1. You can look at that table. You have the number. This is the MF. See here. This is the MF, and remember, this is the odd. This one is even. MF plus minus 2 is 2, right? MF plus minus 4, they're very small. MF plus minus 6 is 0. You didn't plot them. The next one is going to be 2MF plus 1 and minus 1. So look at this is the harmonic spectrum for bipolar switch. Okay, keep this one in mind, and let me see. I want to go to the last part of the single phase inverter. is the unipolar switching. Let's say what's the unipolar switching, and I'll give you one homework. Homework is going to come soon, very soon, maximum by end of this weekend. You know, we're going to have the first homework. We go over the last part of this single phase, inverter. That's what you can. Is here is simulated. Unipolar switch. So the same circuit. We have the full bridge. We have the full bridge inverter. Half bridge is used not that much. Usually we have full bridge, but if you are low power, for some reason you are very limited with your budget, you can use a full half bridge. But usually half bridge is not used that commonly. Always full bridge. And this is the output, right? And it's called A and B. So basically here, previously we said we have one V control, right? This is what we had previously. We said this is a V control, right? And we have a triangular waveform, right? Right? This is what we had. And we said we compare what we had for the unipolar was like this. We said if V control, right, more than VTRI, we said this one is on and this one is on, right? S1 and S4, they are on. If V control is less than VTRI, S2 and S3 they are on, right? Or you can say S1 and S4, they are off, right? This is what we talked about in the last class, right? And these are complementary. If this one is on, this one is off. If this one is off, this one is off, right? This is what we had previously, and we called it's going to end up with this kind of waveform. It's going to end up with something like, here we call it AO, but over there I call it AD, just say that. It's going to be either positive voltage, either could be VDC or VDC half, based on which circuit you have. You have half bridge or you have full bridge, or it's going to be minus VDC, right? This is what we have. Now, in the unipolar, this is one case we talked about it before. Remember the harmonic elimination? We said we could have VDC, 0, minus VDC, right? 3 level of voltage, right? Can you remember that one when we talked about the harmonic elimination? See here I have only 2 level of voltage, 1, 2, 1, 2, right? So the better waveform would be more levels, right? If I have more levels, my waveform is going to get closer to the sine waveform, right? Now, I'll select another. So I'll call this one VCon A. I call this one VCon A. And this is a VTRI we have. So this one is minus VCon A. This is my VB, VCon B. For leg B, I select minus B. So now how the switching is going to work here. If VCon A is more than VTRI, can everybody see here? I don't know if this one is blocking or not. Over there, can you guys see this one here? If VCon is more than VTRI, so S1 is on and S2 is off, right? This is what we had before, exactly like a bipolar switch, right? If VCon A is more than VTRI, S1 is on, S2 is off, and vice versa, If VCon A is less than VTRI, S1 is off, S2 is on, right? That's one case. This is exactly like what we had bipolar. But here, for phase B, we are going to use this one. See, if V con B, which is a minus V control A, right? So you look at here, this is a VA. I mean, by minus 1 is going to be VB, right? If minus V con A is more than VTRI, is a V, basically it's a V con B, right? If V con B is more than VTRI, which switch is on? S3 is on, right? S3 is on and S4 is off. And vice versa. If minus V con A is less than VTRI, S3 is off and S4 is on. You may say, okay, what's the difference between this one and that one? Now let's look at the difference here. This is the bipolar. This is a unipolar. Look at it. That's what I plotted over, right? Here you plotted VAN and VBN based on what I said over there, right? Look at the output voltage here. What is the difference between this one and the previous one? Let me show the previous one one more time here. Huh? No, we don't call it dead time. There's another one. There is a dead time, you know. I'll tell you what's a dead time, you know, but we don't call this one dead time, you know. What is here? Look at here, VO. VDC minus VDC. Or 1 minus 1. Right? Let's forget VDC. It's 1 minus 1, right? Let's go to the other one. Another level is added. Here 1, 0, minus 1. We have a 0 level here also, right? This one is much better than the previous one. Look at the harmonic spectrum here. Look at the harmonic spectrum here. So this is exactly like what we had for the bipolar, but those one was we said is going to be JMF plus minus K, right? And J could be odd or could be even, right? For this one, the odd one are gone. There is no MF anymore. See, there is nothing here. Previous one we had here, right? We had MF plus minus 2MF plus minus 4MF. With this kind of switching, see a simple thing. A simple thing is going to help you. How much is going to help you with the current THC? Just think about it. Now the first harmonic you are seeing is a 2MF, right? Previously we solved the problem. It was a 21. The first harmonic we are going to see. That's the first because there is a plus minus 2. The center harmonic, the first center harmonic will be 21st. Now the first center harmonics is not even 2MF, one less than that. This is the advantage of bipolar switching. You can see here. So basically, if you look at this one to complete this one, I'm going to write it here. Fn. This is the frequency of the harmonics at the output. Is going to be 2 JMF. See 2. I put it 2. Plus minus K times F1. J could be 1, 2, blah blah, and the K is going to be what? K has to be odd. K is odd. No, not odd. No, the K is going to be 1, 2, 3, 4. Odd. So this one is going to be 2J. Think about it. The previous one was a J, right? 1J, this is the 2J. So this is the advantage of this kind of, switching, which we call it bipolar, unipolar switching over the bipolar switching, right? Now, I want to talk about the overmodulation to see what's the overmodulation, and we are done with this part. I'll put it here. Right. So what we have, V1, right? This is the output voltage. For the half bridge, V1 was MA times VDC over 2, and this is the max, right? That was the V1 max is MA times VDC over 2. And for the full bridge, V1 was MA times VDC, right? If for both of them, if MA is less than 1, right? Let's plot it here. What does it mean? What does it mean this one? You know, for both cases. If you look at it, it's this one, right? The maximum of the control waveform is less than the maximum of the triangle, right? Basically here, if you're going to translate this one is said V control max is less than VTRI max, right? Because MA was defined as V control max or VTRI max, right? So if MA is going to be less than 1, means the V control max should be less than VTRI max, right? So if I want to plot V1 versus MA, up to 1, how much is going to be? Let's say this is a normalized, you know, just I want to make it, it's going to be like this, right? Because V1 is equal to MA times something, right? MA times something, right? So this part we call it linear part. And how much is here? This is a normalized, either V1 over VDC. I'm plotting this one for full bridge. V1 over VDC, right? Now, if we go, this is a linear modulation. Now, what is overmodulation? No. See, on some part of your crossing, right? On some part, the V control is more than VTRI, right? If you plot the output voltage for this one, what is going to happen for this case? If you plot it, it's going to be like this. For example, with a unipolar, you know, bipolar, it's going to be some pulses here, but after a while, it's going to be nothing. It's going to be like this. Why? Because during this time, V control is more than VTRI, right? The output is going to be on. During this time, the V control is less than VTRI, right? Output is going to be off. Minus VD, VD. So, but if you look at that one, all the time is chopping, right? If you look at that one, over the period or over the cycle, all the time is chopping the voltage, right? So, basically from this point, the V1 value is going to start to change. It's not going to be any more linear with MA. You know what I'm saying? So this one is going to go, let's see. This one here, let's put it this way. This is the one. From here, this one is going to start to go, it's going to slow down, and finally it's going to get to fixed number. Can somebody tell me how much is this number? Huh? There is no MA value, but how much is this one, the maximum? For example, if this MA goes to very, very big number. How much is it here? Let's think about it this way. If this MA is very, very big, very, very big, it's going to be like this. Right? I mean, it's very big, right? What is going to happen? All the time, this one is more than controlled. Basically, the output voltage is going to be here like this. Exactly. So how much was the fundamental harmonic of the square wave? 4 VDC over pi, right? This is normalized, right? So basically, this number here is 4 over pi, right? That's the final number. From MA, for example, you go to 3, 4, something like that. I'm not sure. Doesn't have a, we look at the net one to see if they have the number. I'm going to find a slide to show you. Yes. Look at here. 1. And this number is 3.24. But this is for MF 15, you know. This number is going to change, you know. If MF is 15 and MA is 3.4, they're going to get to this one. But you can see from somewhere here also it's almost gone there. This is like a square wave waveform from this one. So basically you have the linear part, and this we call it overmodulation, right? Still in the overmodulation they're going to be like this. Sorry, you guys cannot see from there. Here there is some chopping on the side. There are some chopping, but in the middle there is no chopping, right? This is the overmodulation part. And after we get to this point, it's going to be a square wave, right? From this point, it's going to be a square wave. So this one is the linear mode. This is the overmodulation. And this from here is a square wave operation. So there are 3 modes for this one. Usually when we are doing the control, we would like to stay here. You would like to stay in this part in the linear mode. And you will see later on in the control part you are going to design, will ask you to limit the maximum and minimum of MA plus 1 and minus 1. Right? Because MA is like this, right? You're going to be 1, minus 1. We say to keep it there to not pass this mode. Any questions here? So we are done with the single phase inverters. There's one more general things I want to go over. You know, active and reactive power calculation. That's one thing. You know, as a power engineer, you should know about that. You know, what is active power? What is the reactive power? You know, so far you have been a student. You know, maybe use active power, reactive power. But I wanted you guys to see the different way, different approach for the active and reactive power. And let's look at this system. I have a slide for you. I should have we can say inverter, we can call it inverter, or we can put a DC to AC. They show it both ways. You know, these are the for if you want to draw a block diagram, something like that, you can put it this way. Means you are converting DC to AC. Some people they show it with this symbol. They said here is the DC and here is the AC. If you see this kind of symbol, means this is the inverter. DC is converted to the AC. Now here, let me see that we resistor or not. No, I have a resistor. You can have a resistor, but the resistor is going to make it. I call this one IO, and this is the VO. I don't know what they call it here. I think I call this one E. Oh, and this is the F. Now, we have one inverter. This is what you're seeing all the time. All these solar inverter you see at home, they are installed. Usually it's like this. You have one inverter. I'm not sure how many of you guys have solar installed at home. Or UPS, doesn't matter, UPS. Usually it's like that. And here is your home. It could be a battery, it could be a solar, you know what I'm saying? But your home is in the middle. You can feed it from the solar, or you can feed it from the grid. If the solar is generating more than what you need, see this power is coming from the solar here, right? If you are generating more than what you need, the surplus is going to go to the grid. If you are generating less than what you need, the deficit is going to come from the grid. You know what I'm saying? So this is what the solar system works, at home, or UPS system works at home. UPS not, because UPS usually the grid is gone. It's an uninterruptible power supply. Usually they're going to come in when the grid is gone. You guys, you are all familiar with UPS, right? You have some computers, they have important information on them, they shouldn't shut down. They have a UPS unit next to that one. If somehow the grid is gone, that UPS is going to take care of the system, right? But my point is, this is an inverter. Now this load, I'm going to get rid of this load. I'm not going to put it here, because I want to see. Basically, this load could be part of the grid. You know what I'm saying? It's going to be built into the grid. You can send the power to the grid or load here. Now, this inverter can inject the title is active and reactive power calculation in single phase system. Active and reactive power calculation in single phase system. See, I don't care about this part anymore. What is here? What I'm going to look at here, I'm going to assume my inverter is a perfect inverter. It's going to give me a ideal sine wave out. It's not. It's going to have some harmonics. And already with some example, you see the power is coming from the other harmonics is very small, right? So this is kind of approximation of this one. So I'm going to approximate this one with this. I said, hey, I have a VO. This is my, usually they put it this way. Still is the sine, is the AC waveform. But you put it this way, it means that's perfect AC waveform. So we have this VO here, and I'm going to put the phasor diagram here now. I'm going to go with the phasor diagram. This one is going to be what? JXL, right? If I'm going to go to phasor diagram, it's going to be JXL, and XL is L omega. Now, I have two voltages here, right? I'll keep this one as a reference. Whenever in the system you are solving your problem, if you go back to circuit theory, I don't know what chapter was it, 9, 10, something like that. You select one of the voltages as a reference, and you compare all respect to that voltage. I don't know, plus 10 degree, minus 10 degree, something like that, right? I assume this one is my reference. I give it a 0. I assume this one is the reference, and I have E is the RMS or maximum. Maybe we go with the RMS value here. So E is the RMS value of that. Right? So this one we are going to go with the first harmonic, right? It's going to be V1, VO1, right? Is a VO1. I don't know what's the phase of this one. I'm going to put it. Yeah, I give it a phase angle of delta, right? Now, this one is, what is this VO1? This is the RMS value of the fundamental. The RMS value. Now, here I have a current, IO. Right? So I want to calculate, here I'm injecting this P plus JQ. I want to calculate P and Q. How? Can somebody tell me? No idea, right? If I want to calculate the active reactive power for this one, that's the easy one. How we calculate it? You have this is circuit theory, right? You have this, somebody give you this problem. Hey, you are electrical engineer. I have this one, R, L, and for example, C here. How much is the active reactive power provided by this? How do you calculate that? You know this voltage, the phasor of voltage here, and you know the phasor of current here.
It should be times I the active power. It used to be times I the active power.
Those one they had energy conversion. Believe me, they're not answering this question. You know.
B times I cosine of the N.
V RMS or RMS cosine of P, right? Well, you said let's say S is a based on if you go with the RMS, it's going to be RMS, I RMS conjugate, right? And you say P is the real part of S, Q is the imaginary part of S, right? This is what went over it, you know, in the energy conversion, you know, for single phase and three phase system. Let's do it again here. Let's do it again here. I want to calculate the active reactive power for this guy. What should I do? I know the voltage already is VO1 with delta. I should calculate the phasor of the current, right? If I have the phasor of current, I can go with this one. This one times this conjugate, that one times this one. Real part is going to be and imaginary part is going to be Q, right? But before going there, let me write the KVL here. KVL, you said VO1 is E plus JXLIO, right? These are vectors. V, O1, E, and I are vector, right? If you want to draw the phasor diagram for this one, let's start from here. I know E is the E with an angle of 0, right? This is E. And this is my 0 axis, right? A vector with a magnitude of E and with an angle of 0, right? Now, let's say I know, just I'm assuming, I know where is my IO. For example, IO is here, right? And what is this? This is called phi, right? But any angle, you know, just I'm assuming I know where is my IO, right? So how much, where should I put the JXLIO? Whenever we have a J means rotating 90 degrees in the positive direction, right? This is my IO, right? JIO means 90 degrees this way, right? This is the JIO. Right? Time a value, XL, I don't know, whatever is the XL, a number, right? That's a scalar now. So basically I should go to this, parallel with this, or perpendicular to this one. Yes, I'm going to continue this one to see. This one should be perpendicular to this one, you know, that's a JXIO. So this one is a JXLIO. And what is this? VO1. Oh, and what is this angle?
It's your
delta, right? There's a phasor diagram for this case. You know, if the current is lagging respect to the voltage. You know, the current could be leading. Think about it. This current can be instead of here, it should be here, right? Could be leading or lagging, right? Now let's calculate the active and reactive power in this system. So based on what we said, we need to calculate the current first. How much is the current? This one minus this one divided by this, right? It's going to be 0.1 with delta minus E with 0 over JXL, right? So if I'm going to simplify this one, it's going to be VO1 over XL delta minus 90, right? J is in the denominator, it's going to be minus 90. Minus E with minus 90, right? How about I1 conjugate? What's the I1 conjugate?
What about XL?
Huh? Oh, there's XL. IO conjugate, how much is it? Hmm? Is it correct? Minus right? Just the angle conjugate means, you know, either you can convert all the j's to minus j's, or you can reverse the angle, right? You can reverse the angle. Okay, let's continue this one. Now we're going to calculate S. How much is S? Right? How much is the VO1? Times that, right? Right? I put the conjugate value. Let's time this one. It's going to be this one times this one. How much is this one? Delta and minus delta, they are gone, right? If I time this two, it's going to be VO1 over XL with the power of 2 with the power of 90 degrees, right? Which is angle of 90 degrees, minus this one times this one. How much is going to be? It's going to be VO1, right? E, VO1 E divided by XL with how much angle?
Delta plus 90.
90 plus delta, right? 90 plus delta.
Yes, sir.
Yeah.
Can you double check an IO conjugate?
Maybe I made a mistake. Let's see. Let's double check the IO conjugate.
And then negative elements should be just relevant.
Where do you play? Let me see. I can quickly check it here. No, let's see. If we go with this one, it's gonna be, let's say it's in K1. It's in K2, right? This one is definitely correct. Let's check this one. You know, let's check this one. It's gonna be K1 cosine of delta minus 90 plus J K1 sine of delta minus 90. Right? This is what it's out. Conjugate means this one should be minus. Right? So if I'm gonna put that one back to that form, it's gonna be K1 with how much? Let me see. We need to change this minus, we can put it, if I put this minus here, plus here, I can put it here, right? Minus delta plus 90, right? I can do that one, right? And here also this one, cosine of alpha and minus alpha, they're the same, right? I make it from minus and plus, right? So it's going to be K1 with how much angles? Minus 5. What's there? That's correct. No, that's the one I wanted to do. Now, I need to separate the real part and imaginary part of the S to calculate the P and Q, right? Let's put it here. So P is real part of S, right? This is S. How much is the real part of this part? The real part with Y, because this is 90 degree, right? Is how much is the real part of this? So it's going to be this times cosine of this, right? So it's going to be minus VO1 E over XL cosine of delta plus 90. Correct? How much is the cosine of delta plus 90? Minus sine delta, right? So this is a minus sine delta. Minus and minus, they're going to cancel each other. So E, very simple equation. This is the active power injected by this inverter. It depends on what? Think about it. When you have an inverter connected to the grid and you can control it, because you are going to simulate all these things later. And I want you to write about the physical meaning. I don't want you to just write the equation, simulation. I want you to explain what you are doing, to understand. Look at it here. Can I change E?
Yeah.
Why? Why you cannot change it?
Great.
That's a grid voltage, right? But you cannot change the grid voltage, right? Grid is like infinite source, very, very, very stiff source. This one is not under my control. Can I change this L?
Yes, but it's fixed in certain
Yeah.
parameters.
Why not? I can design it initially to select whatever I want. But when I design it, I put it here, I cannot change it anymore, right? This is a fixed number. So this one is not under my control, right? Can I change the VO value VO1 or not?
No.